So in the last video, we had begun this problem and we had calculated the final velocity of the rifle moving to the left to be 1.88 meters per second. We picked to the right to be our positive x direction, and we found that the final velocity of the rifle, V1F, was negative 1.88 meters per second, while the bullet was traveling to the right at 300 meters per second. Now we're looking at another interaction, which is between the hunter's shoulder and the rifle. So the shoulder, we're thinking of these as like discrete, separate things. Really, it all happens together. But if we can imagine the rifle traveling toward a person's shoulder at 1.88 meters per second, we can figure out what the impulse is that's needed to stop the gun. So remember, impulse, you can think of two different ways. One is that it's equal to the change in momentum, and the other is that it's equal to the force times the time. Now we don't know the force or the time, so we're not going to go that route. We're just going to look at the change in momentum. The final momentum is 0, and the initial momentum is 0.800 kilograms times negative 1.88 meters per second. And then we calculate the impulse to be a positive number, and it comes out to be 1.5 kilogram meters per second. Now we can figure out what the force is. I was going to note that the impulse came out positive, and so the gun was moving to the left, but the shoulder provides an impulse that is to the right in order to stop the gun. And this will make even more sense perhaps when we calculate the force. So we know that impulse is also equal to the force, which is a vector, times the time. So the force is equal to the impulse divided by the time. So that's equal to 1.5 kilogram meters per second divided by 3 milliseconds. So 3 milliseconds times 1,000 milliseconds in 1 second, just like there are 1,000 millimeters in a meter. And so this is 0.003 seconds. And this comes out to 500 newtons. Okay, and that's also a positive number, and that makes sense that the shoulder would push to the right on the gun in order to stop it. The next problem, we have a 5 kilogram bullet, and it is impacting a target. So the bullet's going 300 meters per second. That's how fast it was going in the last problem. It's hitting a target that was stationary. And we're going to figure out, well, what's the speed afterward? All right, so here we go. We've got V1I, 300 meters per second. And then we've got V2I, which is equal to 0. And here, let's just go ahead and write out our momentum conservation equation. Okay, now it doesn't actually appear on your equation sheet like this, because this is an isolated system. So we've drawn a box around the system. That's what's the system initial. And this is our system final. There's no external forces. We're not worrying about friction from the table, and because we're taking our time frames to be as close as possible together. This is just before the collision, and this is just after. Okay, you can think of it like a billionth of a second before the collision and a billionth of a second after the collision. And so therefore friction doesn't have time to really factor in. Okay? Or, if you prefer, for right now just consider it to be a frictionless table. But really, this idea of just before and just after, that's why we don't have to worry about the friction from the table. Alright, so it's an isolated system, so that becomes 0, and then we get m1 v1i plus m2 v2i equals m1 v1f plus m2 v2f. Alright, now we know the block is stationary at the beginning, and we look here and we say, okay, well, we know this mass, and we know the other mass, and we know this velocity, but that leaves us with two unknown velocities. So one equation, two unknowns. But wait a minute, there's not actually two unknowns, only one unknown, because these two things are connected, they're moving together, and so we can say that v1f equals v2f, and we could just call it vf. So then we can put in the values here. We can say 0.005 kilograms times 300 meters per second equals 0.005 kilograms times vf plus 0.800 kilograms times vf. Put parentheses around those just so they stand out a little bit more. And so then we have 0.005 kilograms times vf plus 0.800 kilograms times vf. So on the right side, we get 0.805 kilograms vf. Okay, and that might be a little surprising for some of you. But remember, if we had, 5 vf plus 6 vf, that would be 11 vf. We just add together the coefficients in front, and that's all we're doing here. Just they happen to be decimal numbers, but we can do just the same. All right, and so we get 15. Let's see. That's 15, and we divide, so that comes out to 1,500. 1.5 kilogram meters per second. Divide both sides by 0.08 kilograms, or 0.805 kilograms rather, and we get VF and I just noticed I made a mistake here. This is a 500 kilogram target. Okay. So just making sure everybody's paying attention out there. Now, that was an honest mistake, but it is a check on whether you were paying attention or not. Hopefully you were questioning me on that. And so I'm not going to take this out of the video. I like having these mistakes in there because I really do want you to be thinking about each step as I go. And so we divide this out and we get 2.97 meters per second. It makes sense that the combined speed is going to be a lot slower because we have a small bullet hitting a rather large target, or a relatively large target. So that makes sense. It's also a positive number, and oh, I forgot to say it, to the right is our positive x direction. Alright, here we go. Now the target is in motion. So we've still got our bullet, v1i equals 300 meters per second, but our target is moving at 5 meters per second. To the right is our positive x direction, so these are both positive. Okay, and we're supposed to find VF, and that's going to be a common VF. So this is initial and final, and so we can apply our conservation of momentum equation. M1 V1I, 1I plus M2 V2I equals M1 V2F plus M2 V2F. I wrote it down just as it appears on our equation sheet, remembering that all these velocities are vectors, and now we can fill in the values. 5 grams. Notice I'm putting in the values of mass in grams this time. And I want you to see that it works out okay. This time, the initial velocity is not 0, so we have to make sure we enter it here as well. There's a positive value. 5 grams times VF plus 500 grams times VF. So I've substituted VF in for this value and this value. So now I get 1500 gram meters per second plus 2500 gram meters per second equals 505 grams times VF. This becomes 4,000 gram meters per second. Divide both sides by 505 grams. And we see that the grams cancel out. So it didn't matter that we stayed in grams. Sometimes it really matters that you make the unit conversion, and sometimes it's not so important. This is one of those cases where it's not so important. In fact, it would have just wasted time to do the unit conversion. And in fact, it did waste time on the last slide, but I wanted to show it to you both. One where I did the conversion and one where I didn't. Get the right answer in either case. And in fact, I encourage you to do this problem, redo this problem, but convert everything to kilograms, and redo this last problem, but work everything in grams. Both of those problems will be quite quick to redo, and then you would be convinced that if you keep track of the units, you'll be all right either way. Here we have a similar problem, except that the target is moving toward it at 5 meters per second. So if to the right is our positive x direction, that means this V2I equals negative 5 meters per second. And so we can start with our conservation of momentum equation, and then I would write out the full equation here from the equation sheet, M1, V1I, etc. I'll just go ahead and fill in the values. 5 grams times 300 meters per second plus 500 grams times negative 5 meters per second equals 505 grams times VF. And so we get 1500 gram meters per second minus 2500 gram meters per second equals 505 grams times VF. Divide by 505 grams. So we're going to take this, we're going to get negative 1000, and then negative 1000 divided by 500, that's just about 2, well, negative 2. And it comes out to be negative 1.98. In this case, both the bullet and block are moving to the left after the collision.